This is a tutorial on how to use the CloudRF API to automate the generation of airspace analysis layers focused on altitude, not signal strength. In front of us here we have a air surveillance radar with a 100-kilometer radius, which we've modeled using our API, and the colors here denote altitudes. You can see on the key in Google Earth different altitudes with different colors, and this is a 3D layer, so we can actually see how the topography affects radar coverage right out to 100 kilometers. Now, as you might imagine, making these can be quite laborious, which is why we've created a script to automate the process using our API. So that script is available on our GitHub repo, and if you go and have a look there in the CloudRF API client's Python folder, it's a new program called 3D Airspace. And in this program you get a Python script and some JSON templates, and what we can do is use a JSON template such as the air surveillance radar here, which is a .json file, and we can create our system. This system could be a radar, it could be a counter-drone system, and it could just be line of sight, and you just want to see how much of the sky you can see from a given point. So in this template here, this is a normal CloudRF template. All the settings here are defined in our API. We prepared a very high power long range air surveillance radar with altitude ceiling of 10,000 feet here in the receiver section, and the height units are feet above mean sea level. So we're caring about barometric altitudes here for an aircraft as opposed to above the ground, which we'll do later. To use this then, you have to put your API key in as an environmental variable, and then you call the 3D Airspace script and the JSON template. That's quite simple, and now what it will do is it will split up that 10,000 feet into groups of 10, so 10 buckets of 1,000 feet each. Each one is running through the API here. We're at 5,000 feet already, and you can see the elapsed time in milliseconds on the right, so GPU accelerated. It's pushing it through very fast here, out to 100 kilometers each time. And finally, we're done. We've analysed those layers and we've created that KML. So that's the one you can see in front of you here. The radar and the settings that we used are also available inside the KML here if you click on the center point. So that's a large one. That's an air surveillance radar. That's useful if you care about hills, but if we want to bring the resolution right down to an urban level and do a counter-drone scenario, that requires quite a different template. So let's go and have a look here. We'll see what demo we've got. Let's go and find the drone. So here's the drone. It's the Dodgers Stadium in LA, and this time very different scale. It's Wi-Fi frequency. Height ceiling is 120 meters above ground level, or 400 foot. And if you see the height units that we're using here down in the output section are meters above ground level. So this time, instead of a barometric altimeter, we're looking at a GPS altitude above the ground. And we're also using a different model here. This model is the ITU 1812, or in US standards TSB 88 model, and that's good for 2.4 gigahertz. This is a very high resolution urban one at 4-meter resolution, 2-kilometer radius, because you're not going to be detecting Wi-Fi much further than that in somewhere like LA. So let's go ahead and run this demo now with the drone. And this time it will split that 120 meters up into 10 again, so very low altitudes this time, above ground level. It's pushing it through nice and fast, even with the high resolution LiDAR we have for cities in the States. And finally we're done, and we can go ahead and open up that file. I'm just clicking around on the other screen here. Let's go and find it. Python 3D Airspace and 3D Radar KML. So there we have a KML at the Dodgers Stadium. Because we've got Google Earth, we can put on the 3D buildings, and we can see the radar is over here to the northeast, and there's all the settings, and you can see the coverage is quite asymmetric. We've got good coverage over to the southwest here. We've got poor coverage to the south because of the obvious obstacle, and if we zoom in and tip the map, you can see for a terrain following aircraft here, you can see where you can and cannot detect that drone at different altitudes. So it's looking at the problem from a different perspective, and you can actually see where blind spots are in your system, and surprisingly they can be quite close depending on the topography. So that's 3D airspace analysis, and there's a free Python script to do that quickly for any template that you can imagine.